So taking a look at some of the applications that we might come across where we can use the net change theorem, we find quite a few. I mean, there's a lot of things that we can do with this net change theorem, and we jump into a couple of these right off the bat. So let's just take a look at this first example. A red car and a blue car start in the same position, and the red car has a velocity of f of t, and the blue car a velocity of g of t. If they drive in opposite directions, how much distance is between them after 4 hours? A lot of times students get a little overwhelmed by these type questions, and it can be, it can be frustrating. So I like to draw a picture, right? And so I've got this starting point, right? Here's the point at which I'm starting. And one car is going to drive in this direction for 4 hours, and that's going to be given by f of t. And this other car is going to drive in the exact opposite direction, g of t. So yeah, I'm having a hard time drawing these straight lines with my pen. Y'all forgive me. So we're going to go a straight line like this. So this guy's g of t. And the question then becomes, what is the total distance that's been covered, right? What is that total distance there? Well, what we're going to do is we're going to integrate g of t, right? Integrate g of t for 4 hours. So if you look, g of t is the velocity. Okay, so we said that if we integrate velocity, we get the distance traveled. And then we're going to add that, we're going to add that to what we get when we integrate from 0 to 4 f of t dt. Okay, so this is how I'm going to find that total distance traveled. I'm going to integrate the f of t and the g of t part. Well, look right here. We can see that if I integrate from 0 to 4 of f of t, okay, and you can follow the math here, we get 88 over 3. So this is the amount of, this is the distance that was covered by that red car, that first car there. And then I can follow the math and do the same thing for g of t. So again, having that picture there and being able to kind of visualize what's going on is really, really important. And again, you can follow the math here, the integral of g of t, evaluated at 4 and 0, we come up with 52 over 3. So the total distance traveled is 88 over 3 plus 52 over 3. This is the total distance traveled, which is 140 over 3 miles. Here's another one that's kind of similar. The velocity of a particle is given by t to the fourth plus t meters per second. Use the fundamental theorem of calculus to find the distance traveled in the first 8 seconds. So there's nothing really that tells us whether this is displacement or total distance traveled. So because it says the distance traveled, I want to make sure, and I'm going to go to my calculator, to my graphing calculator, and I'm going to say, what does it look like when I graph t to the fourth plus t, right? You can see t to the fourth plus t. So if I go to the graphing calculator, I'm going to plot t to the fourth plus t. Excuse me, this needs to be x, right? There we go. So x to the fourth plus t. Now look, they gave me an interval in the first 8 seconds, right? So we're going to begin at 0 and go all the way to where our x value is 8. So if you look at that, look at it in terms of that 0 to 8, none of this is below the x-axis, okay? So when I'm integrating 0 to 8, I don't have to worry about, is there anything that I have to take the absolute value of? This is just a straight integral like so. All the parts of that graph that were below the x-axis were back there behind 0, and our analysis started in the first 8 seconds. In other words, when time was equal to 0 out here to 8. So again, following the math here, right, we're taking the integral of t to the fourth plus t, that's 1/5 t to the fifth plus 1/2 t squared, and just plugging in 8 and 0. These are some big numbers, right, but Newton will tell you what to round to so that you can identify the correct answer there. So here's a problem that looks it looks a lot different, but it's pretty much the same thing. So Stacy starts putting water in her pool at noon and stops at 1 p.m. So the total time, that's 1 hour. She fills the pool at a rate of T minus 5 gallons per minute. So here's the thing, in terms of our last problem, right? G of T would be T minus 5. Now there's something significant right here in the units, and that's gallon per minute. So she was filling the water for 1 hour. Well, I can't put my interval as 0 to 1 because that time is in terms of hours and my rate here is in terms of minutes. So I'm going to convert the 1 hour so that it's not 1 hour but instead 60 minutes. Okay, so that's where we get the 0 and the 60. We're going to plug those in after we take the integral, and we pumped 1,500 gallons of water in there over that 1 hour. So what's really important is this word rate, right? And that's where that net change theorem comes in. We're integrating the rate to find the total accumulated amount, right? At a small town intersection, pedestrians use a crosswalk at this rate per hour, right? If T equals 0 at 6 a.m., how many people cross between 6 and 9? So if T is 0 at 6 a.m., then 9 would be 3 hours. So it may be a little confusing with where they got 0 and 3. The interval that we're looking at is a total of 3 hours. And then again, this rate, right, that keyword rate is what's important. That's the thing that we're going to take the antiderivative of. And so if we plug those values in and simplify, we get a total of 3, right? 3 people cross the intersection in those 3 hours. So you'll find, if you're riding along the highway, at least they do this where I'm coming from, you'll have a stretch of highway, and every so often there'll be a little cord going across the highway, and really all they're doing is to see, over some period of days, how many people are using that highway, how many people per day are using that highway. And that's just one of those studies where they want to see, which highway should we resurface first, right? So these rates, right, this is an example of a rate when I have something per something, in this case, people per day. Here's another rate when I have people crossing per hour. So you'll come in contact with this net change theorem quite often in a real world context. So take a look at these problems in Newton, and let's see if we can't get you the help that you need.